Welcome to February 3rd, lesson number 3. So today we're going to talk about collision theory. Now, we talked briefly about collision theory yesterday, and today we're going to flesh it out a little bit more. And this is also collision theory is also what's referred to as reaction rate theory. And in order to talk about either of these, we also need to review what the kinetic molecular theory is. Now, the kinetic molecular theory, this is the idea that molecules can't actually react with one another at a distance. All right, so if I have a molecule over here, and let's say I have another one over here, these two molecules, I'll make this one red, they can't actually react with one another until they're in closer proximity. All right, so with the kinetic molecular theory, it requires that molecules are traveling and then they're actually making some contact with one another. So I'm going to try a few new things with this lesson. I'm going to try, instead of writing, I'm going to try to actually type, and hopefully that'll look better. So first of all, let's talk about what the collision theory states. Okay, so collision theory. So if we have a chemical sample, and this chemical sample consists of particles. Now, when I say particles, I mean like molecules, atoms, or ions. Alright, so they act as small, hard spheres that collide and bounce off of each other. It's like if you're throwing a bunch of like basketballs at each other, right? Like there's gonna be some energy release when they hit each other, and then when they rebound as well. So when they bounce off each other, what's gonna happen is they're gonna transfer some of their energy among themselves and also into their surroundings during the collision. Alright, so this is the first set of notes here. So a chemical sample consists of particles, and they act as small hard spheres that collide and bounce off each other, transferring some of their energy amongst themselves. So in order for a collision to be effective, and so if I had a collision between two molecules, and for this collision to be effective, so for example, if I had this molecule over here and this molecule over here, in order for it to be effective, first of all, they would need enough energy, but they'd also have to be in the correct position. Alright, so sufficient energy and correct positioning is important. Let's put that down. So two things are needed for a successful collision. All right, the first one being sufficient energy, right? So sufficient energy. They need to be able to make it to one another and have enough energy to actually collide. Right? You can think about rolling two basketballs to each other from across the gym, and you're standing on opposite sides of the gym. If you don't have enough energy, those balls are never going to make it. The second thing you need for a successful collision is correct positioning. Now, the reason you need correct positioning is if we think about molecules or compounds and sets of atoms, then remember that all atoms are different. And so with that, I'm going to put that set right here. With that, if I have an atom here that is exactly the same, so let's say I have a bond between two atoms, and this bond, so these two over here, This is one molecule, and then I just have an atom over here. Now, if this collides with this atom, so this part of my molecule collides with this atom, there's not going to be an effective collision because of correct positioning. What would be better to have instead of that is rather than having the molecule on that side, it would be more effective if this molecule was attached on my opposite side over here, right? Now the reason being is, rather than having two molecules that are the same collide with one another, if I have this molecule, or this atom, and this atom collide with one another, that's going to result in an effective collision. Ineffective collision, so if it was the other way around, then an ineffective collision would result in just these two particles rebounding off each other, and there would be no change in their chemical structure. So in order to just highlight that, I have this graphic here. Now what it shows here is a reaction between NO and O3, and it shows what an effective collision would result in and what an ineffective collision would result in. And so first of all, if I have my NO over here, like if we take a look at the ineffective collisions. Now the ineffective collisions in these cases are mostly a result of incorrect positioning. And so you see here you've seen oxygen just colliding with another oxygen, and this is going to be ineffective because it's colliding with an oxygen. First of all, it's an oxygen hitting an oxygen, so we're not going to have a reaction resulting. But it's also colliding in a place where this oxygen isn't going to the bonds aren't going to break between these other two oxygens. All right, so if I look at this oxygen right here and this oxygen here, when I hit this middle oxygen, there's not going to be a destruction of bonds, or not a destruction, a breaking of bonds. So we're not going to have any new bonds forming. And it's the same thing that's going on over here. Above, it was more a result of oxygens colliding with oxygens, but in this case, we do have our nitrogen right here colliding with our oxygen. But again, it's in a position which is not going to be effective because it's hitting the middle oxygen. But if we look at our collision in the bottom here, I'm just going to highlight our effective collision right here. This will be effective because if we look at where our collision is occurring, it's occurring with a nitrogen and an oxygen, and it's also a nitrogen and one of my terminal oxygens, one of my oxygens that are at the end of my molecule. And so this is going to result in an effective collision. We have enough energy, we have sufficient energy, and we have correct positioning. And so this is going to be good. Right, so those are the two things you need to look out for is the correct positioning and the amount of energy that is needed in order to break the bond. Now, what we want to talk about is enthalpy. Now we talked about enthalpy. Well, we have been talking about enthalpy briefly, and what we want to talk about is enthalpy changes. Now we talked about this a little bit in Chemistry 11. It was more as an introduction. Let me just fix that typo there. So enthalpy. There you go. All right, so when we were talking about it in chemistry, we pretty much just referred to endothermic and exothermic reactions. In order to really understand enthalpy, we have to understand what is happening with energy. Now, yesterday we talked about kinetic energy, and we also talked about potential energy. Not kinetic energy, potential energy. Okay, so first of all, let's just have a quick review of what kinetic energy is. All right, in Greek, remember, kinetic has to do with motion, so it's a form of energy that's related to the motion of something. And in this case, when we're talking about chemistry, it's related to the motion of a particle. So kinetic energy is the form of energy related to the motion of a particle. Okay, so that's kinetic energy. Now, we also need to in order to really understand enthalpy, we also have to discuss what potential energy is. Now, potential energy, remember, potential energy is you can kind of refer to it as the potential of something to give off or take in energy. And so this is a stored form of energy. So stored energy. If you recall, in physics, the formula for determining what kinetic energy was 1/2 mv squared, right? 1/2 times the mass times the velocity squared. And what that means is for something to have kinetic energy, it has to be moving, it has to have a velocity, right? But it's not the case with potential energy. Potential energy is stored energy. That being said, when we're talking about chemistry, this is the type of energy that exists as a result of position of a molecule. So it exists as a result of the position of objects. In space. Now, if we think about the formula for determining potential energy, remember in physics, that formula was potential energy was equal to the mass times the acceleration due to gravity, so 9.8 meters per second squared, times the position. Right? So the potential energy was determined by the mass of your object and the position, mostly. All right, and so repulsive and attractive forces for potential energy are what are going to determine what make up the object. And so this is directly, in chemistry, the potential energy is directly related to the energy of the electrons in the chemical bonds. Okay, so it's related to the energy of the electrons. E minus is short form for electrons in the chemical bonds. Now it's also related to the number and type of atoms in the molecule. So this is potential energy. It's also related to the number and type of bonds. So what do these have to do? What does kinetic energy and potential energy have to do with enthalpy? Well, I'm just going to scroll up here just a little bit. Enthalpy, then, is the total kinetic and potential energy of a system under pressure. All right? So enthalpy is equal to the kinetic energy plus our potential energy of a system. Now, keeping all of that in mind, to make all these changes in energy easier to keep track of, what we need to do is find the change in enthalpy. Right, so yes, we know that it's the sum of the kinetic energy and the potential energy, but one way we can also discuss enthalpy, or in this case our change in enthalpy, is the enthalpy of our products. That's supposed to be a U, minus the enthalpy of our reactants. Now, as you know, this symbol delta, that means changing, right? And so delta changing always means final minus initial. So in this case, if we're talking about a chemical equation, it's the products minus the reactants, where the enthalpy of the reactants is the combined enthalpy of all the reactants. All right, so the enthalpy of our reactants is the combined enthalpy of all the reactants, and the enthalpy of the products is the combined enthalpies of all the products. Next thing is kind of just review, is when we're talking about endothermic and exothermic reactions. Remember, with an endothermic reaction, let's go this. So with an endothermic reaction, as opposed to exothermic, an endothermic reaction is when energy is absorbed by a system from the surroundings. All right, and so if I were to compare these two, and I'm going to use a little graphic in order to do that. So if I were to compare endothermic with exothermic reactions, if I use this system here, so in the middle here, this is our system, and in the middle is my system for both of my different types of reactions. And on the outside here, this is my surrounding. And same thing over here, this is my surrounding. Now, if we're talking about where the energy is going, in an endothermic reaction, my energy, so if I have energy out here, the energy is going from my surroundings into my system, right? So it's absorbing, my system is absorbing my energy. In my exothermic reaction, remember that our system is the one that is giving away energy. And so our energy is going from my system into my surrounding environment. And so let's think about what this means for our potential energy or kinetic energy of our systems, right? Like if we're talking about our endothermic reaction, we have energy going into the system. What that means is it's going to result in an increase in potential energy. So the products are going to have more energy than the reactants. And there's going to be a loss of energy from the surroundings, and that's going to make our systems feel cooler or cold. In endothermic reactions, the energy you'll see is in the form of heat, and that enters the system. All right, so that's going to be on the reactant side of your equation, and you'll end up with a positive enthalpy. All right, so your change in enthalpy will be positive. You'll have a positive enthalpy, and that means that for the change in enthalpy for a exothermic reaction, that would result in a negative value for your enthalpy. And another thing is that what's going to happen for your, so we have endothermic on my left side here, but that's also going to mean that you are going to be putting in energy to make the reaction happen. So for this reaction to happen, it will require energy, and the energy will be on the reactant side. And it's going to be the other way around for our exothermic reactions. Remember, we have a negative enthalpy, and the products will have less energy than the reactants, and that also means that our energy will be on the product side for exothermic reactions. Alright, so this is just a quick review of enthalpies. For the rest of the class, what you need to do is just read pages 17 to 25, and then I want you to begin working on questions 18 to 28. That's 10 questions there.